All right. So last class, we left off working through a few examples of building confidence intervals for sample means. All right, and we're using this equation. Okay. So we're building our confidence interval around that sample mean. We're going to add a certain amount to it, or this kind of margin of error, to get our upper bound. We're then going to subtract that same amount to get our lower bound. Right? We can do this for different levels of confidence. Different levels of confidence correspond to different alpha values. Those alpha values kind of represent the area outside the interval, or we can think about this as the area in our tails, right? If we think about this like a normal distribution. Once we look up that z value, we then need to multiply that by, okay, well, if it's 2 standard deviations away, I don't just add 2, I add 2 times whatever the standard deviation is. Well, the standard deviation of our sample means is equal to this equation. So we can first solve for this and then just plug it in, or we can do it all kind of at one time, right? So that's where we left off. Oops. So we have these different levels of confidence we want to be able to say things with. They correspond to different alpha values. We worked through a few problems up here. So what we're going to do today, before we go to proportions, let's just do a little bit of work and kind of start out in Excel. So on Canvas, it's the wrong folder. Sorry about that. There's this confidence intervals example file. So we were dealing with situations where we knew what the population variance was, or we knew what the population standard deviation was, so known standard deviation for the population. Probably, we might get there a little bit today, but definitely on Friday, we'll talk about what happens if we don't know the standard deviation. But for now, we're thinking about examples where we do know what it is. So let's blow this up a little bit, and we'll start doing a little bit of work in here. Okay? So I have this enrollment data for what looks like 111 different schools. Let's just say, right off the bat, I used the variance for the population here. Now, this is just a sample. You would have to be given what the population variance is on an example like this. So let's say I just gave you that population variance, right? 68 million. You could find the mean for the total enrollment across your sample by simply using that average function, right? Hopefully that's nothing new. We can use our sample size, right, by just using that count function. So another way to think about the sample size, right, that's n, okay? I'm just gonna right align that. So remember, n is the sample size. We then go down here. So this is where I'm building my confidence intervals. So generally, this won't be here, right? But I'll always set up these confidence intervals this same way because it makes it a lot easier to do multiple different values for alpha pretty quickly, right? So here I've got the 90, the 95, and the 99% confidence level, right? So just as a reminder, if I right click here and insert another column, 90, 95, 99% levels, right? I'll actually even, let's throw some percent signs in there. Just to kind of remember what levels of confidence correspond to what alpha values. So in the examples we worked through on Monday, we actually would take alpha, right? Remember that we divided it by 2 and then went to the table to find that z value, okay? Well, we can do that in Excel. In fact, we've actually already looked at the function. So the function that does that in Excel for us is that norm.s.inv function, okay? If we tell that function the area we want in the lower left tail, it returns to us the z-score that would give us that area, right? Well, what's the area we want in the lower left tail for confidence intervals? Just alpha divided by 2. So I take alpha and I divide it by 2. Now the problem with this is it's always going to return to me a negative z value. And we kind of mentioned last class, when we looked that value up in the table, right? The positive and negative sign are really already built into the confidence interval equation because what we're really thinking about doing here is we're going to be going a certain number of standard deviations to the left to get that lower bound and a certain number to the right to get the upper bound. So this area was alpha over 2. This area over here was also alpha over 2. Now, I can do this 2 different ways, right? I know that if I just look up alpha over 2 in the table, or using that norm.s.inv function, it'll always give me the negative z-value that I want, right, to get the lower bound. Now, in Excel, one way we can get rid of that negative sign is simply taking the absolute value. So I'll show you how to do that first, but before we go back to Excel, the second way we could look it up is if I want to find the positive z-value, if I know the area to the right is alpha over 2, I know the area to the left is just 1 minus alpha over 2. Okay? So I can do it either way. I can just take the absolute value and look up alpha over 2, or to get the positive z-score, I can just look up 1 minus alpha over 2. So if we go to Excel, oops, there we go, right? I could have just done 1 minus alpha over 2, and it gives me the same score, but it drops the net, right? It gives me the positive value. Now, just to prove to you, if I would have done norm.s.inv and done alpha divided by 2, not 22, by 2, I could have then just taken the absolute value of that, or ABS, right? So whatever I put in this ABS function, it'll essentially just drop the negative sign, okay? So if I hit enter there, sure enough, it gives me the exact same value, right? So whichever way you want to do it is fine. They'll both give you the same answer, right? So let's use this way first, right? Where we're just doing 1 minus alpha over 2. I say first, that's the one I'm going to stick with. I've already shown you both, right? I'm not going to do it twice. It'd be the exact same way if I had used that absolute value. So if I copy this down, what it's going to do is it's just going to update that cell reference for what alpha value I wanted, still divided by 2, right? And I can get a bunch of different z values, and I could do whatever alpha I want here. I could do, I don't know, 0.23, right? And it gives me that z value, right? So I can use whatever alpha values I want. From here, it's really just using Excel to be a calculator, right? So to get the lower bound, we had that equation, which was take my sample mean, subtract, because we're doing the lower bound, whatever the z value is, times, and here, the square root of the population variance I was given divided by my sample size, right? I'm just using Excel to do what I would do in a calculator here. Right? Now, the one reason why it's a little bit nicer to do this in Excel is because if I want to do this for several alpha values, I'm using all the same information, the same formula. The only thing that changes is I'm using a different z value, right? So I want the z value cell reference to update when I copy this down, but I don't want anything else to. So I'm just going to throw dollar signs in front of everything else, okay? Once I do that, now when I copy this down, I've got my 3 lower bounds. And notice, when we go to higher levels of confidence, right? Higher levels of confidence mean that alpha is getting smaller. So it means I want a smaller area in my tail, which would mean the z-score has to be further away from 0, right? If the z-score is further away from 0, when I plug that in, I'm adding and subtracting a larger margin of error. I'm going to get a wider confidence interval. So my lower bound should be lower at higher levels of confidence, which it is, and my upper bound should be getting higher at higher levels of confidence, right? Widening my confidence interval, okay? So there's a couple ways we could copy this over. Now the problem is if I just try to copy this, what in the world? Oh yeah, it's updating that z-value cell reference. I don't want that to happen. So what I could do is, now that I've got this working okay, I could put dollars, well, I don't know why I'm doing it up there. I could put dollar signs in front of that z-score cell reference, copy it over, should get the exact same value because nothing should change. But now I want to, instead of subtract, I want to add that margin of error here, okay? So if I do this, the problem is now if I try to copy this down, I don't want this, I want my z-score to update. So now after I've copied it over once, I can get rid of those dollar signs around that cell reference. Now, if I copy this down, it's using the correct z-score, right? Now, another way you could do this, if I click here, I highlight this, I'm gonna hit Control-C just to copy it. Now I hit enter to get out of that cell. If I go here, and let's say there was nothing there, right? And now I paste it, or Control-V, and I think on a Mac it's probably Command. Now nothing's, oh, sorry. Let's get rid of these dollar signs so I can show you that it actually works, even if you don't freeze the cell reference. So let's say this wasn't here. I could have highlighted this, copied it, hit enter, go to this cell, hit Control-V, and notice if I do it that way, if I don't drag it, it doesn't update that cell reference. Now the only thing I need to do is change that negative sign to a positive sign so I can get the upper bound. So there's two different ways, of doing the same thing. All right? So now I drag this down. Now I've got my lower and upper bounds for any level of alpha, right? I could do this for 100 level, well, I could do this for whatever levels of alpha, right? If I wanted to add in another 3 here, now I would just be copying things down, right? But I really only had to enter things in on this first line, okay? Any questions on that? You want to see one of those cells again, or we're okay with that? I know we went over that example at the end of last class, kind of quick, where I had the same sort of setup, but I actually was able to see what that population data was. So I knew what the true mean was. I then took 1,000 different samples, and that's really what I was doing down here. Once I found the sample mean, I found the lower bound. Now here what I did was I only chose one level of alpha. I could have probably looked at, I could have created a cell reference here and put that in the cell, and then we could have played around and changed it. So actually, I think I'm going to do that here just to kind of prove to you. So let's say I went up here. I'm going to put alpha right here. Whoops, yeah, right here. There's nothing there yet, so I'm going to have some issues, but I'll label this. My alpha is going to be up in K3. Okay. So I go down here, my lower bound. I'm going to want to make sure that this doesn't change. All I did was, instead of first finding the z-score, I just put that into my formula, right? So notice here where there's this norm.s.inv, on the other example that we had, I was first finding the z-score and then selecting that z-score. So all I'm really doing is, instead of using a cell reference for the z value, I'm just essentially copying that into the formula, right? And that should return to me the same thing, right? So either way, this, the second way I'm showing you just cuts out a little bit of the kind of intermediate steps. But I want to show you the intermediate steps because a lot of times that's how you can like track down where your error is, right? If instead of 1 minus alpha over 2, I forgot and just use alpha over 2, well, I can't see that that's where the error is occurring if I'm putting everything on one line, right? So breaking it down in intermediate steps is probably the best way to do it if you're trying to like make sure, if you're not real confident in your use of the formulas yet, okay? So once I had this, oh, what doesn't it like here? Norm.s.inv, oh. First of all, I need to do alpha divided by 2. I don't have a value up there yet, so that's why it still doesn't like it. So we'll go up here, and let's say we'll do that 5% level, okay? So now it likes this, right? I'm gonna do the same thing down here. I'm just gonna use my cell reference instead of putting in alpha over 2, that way I could change it. All right, and now I have to scroll over. It's going to take a second. I'm just going to copy all these over. And there's definitely a shortcut to do this, but I'm just going to show you how to do it this way. So we drag over. We got to go all the way over to 1,000. Hopefully we're getting close. Just went a lot faster in my office. Let's stop here. Oh, I forgot to freeze something. God bless it. What didn't I freeze? Didn't freeze my cell reference here, right? So I'll freeze that, and we keep using the same alpha values. Let's see, I think I can. Let's try to copy this over. paste my formulas. There we go. And now notice I've built confidence intervals for every single one of my samples. I then check to say, okay, does this first sample that goes from 74 to 82, does that include the true mean of 79.8? Sure enough, it does. So there's a 1 here. Does the next one, 77 and 85? Sure enough, that includes 79. Let's go over to 1. 71 to 79.2 doesn't quite include my population mean. So basically, I then just counted the number of times that my confidence interval from my sample mean included that true population mean. And notice, it's going to be a little off because we don't have an infinite number of samples, but every time it generates new random numbers, right, they're always right around 95, right? A little bit above, a little bit below. If I had a truly infinite number of samples, I get exactly that 95% of my sample means had a confidence interval that included that true population mean. Then if I wanted to, I could play around with this. Well, what if alpha is 0.1? Now notice, now I'm getting about 90% of them, right? Keep getting new, keep getting new random numbers, right? And now it's kind of right around 90%, okay? So that's how we can construct these lower upper bounds in Excel. If I was working on kind of an assignment where I'm doing this, I would base it off of this one, where I break it down into intermediate steps. I think that's just a little bit easier way to see it. And then we can do the exact same thing for sample proportions, okay? So go back to the slide. First of all, before we go back to the slides, are there any questions over any of that in Excel? You want to see another cell again? Good, okay. So go to the slides here. Now, when we're talking about the population proportion, remember we said the mean of my, when we were talking about sample proportions, the mean of my sample proportion is my population proportion, right? And the standard deviation was equal to this. Well, the problem is, if we're taking a sample and all we have is the sample proportion, how do I know what the true population proportion is? That's the whole reason why I'm building this confidence interval is I can't observe that, right? So what we're gonna do is we're gonna estimate that with the information we have, which is just the sample proportion, okay? So the standard deviation of our sample proportions, we're gonna be estimating with this, okay? From here, right, as long as this criteria is met, which once again, I won't give you examples where this doesn't hold, but just to kind of be complete, we would have to make sure that if we had a low probability of something occurring, we need a high enough sample size that's above 5 in order for our confidence intervals to be accurate. But I'll never give you examples where this isn't true. So notice the confidence interval for our the confidence interval for our sample proportion is a very similar format to the sample mean, right? So let's think about why, right? If I can get a, so all we're doing with the confidence interval for our sample mean, add, subtract. Now this was our standard deviation of our sample mean, which we knew was equal to the square root of the population variance over the sample size. For the sample proportion, well, we're going to be building our confidence interval around not a sample mean, but our sample proportion. We can still use that standard normal or that Z distribution or Z tables. But now, and I'll get out of the way here in just a second. Now we're going to be multiplying that by, well, being 2 standard deviations of our sample proportion away. Well, what was the equation we had for this? Well, that's the square root of the sample proportion times 1 minus the sample proportion divided by our sample size. Right? But notice it's really following the same kind of format. I take the sample statistic I'm interested in, I'll then add or subtract how many standard deviations away I want to be times whatever that standard deviation is. It's just that different standard deviations, we've got slightly different formulas for calculating, right? Depending on what sample statistic we're looking at, okay? Any questions on that? Trying to really connect these two so I can show you, like, this should just be the same process now. Slightly different formula, but same process. So, okay, I was gonna say. You got worried I didn't start the recording there for a second. So now, I said, I think last class, I refer to kind of what we're adding and subtracting as the margin of error. You really are only supposed to do that when we're talking about proportions, but I think it's easier to have a term for what we're calling that with sample means as well. So we'll think about this as our margin of error, okay? So let's say we have this example where I get 81 people surveyed, and 63 out of the 81 say they what? They favor covering pre-existing conditions, right? This was a poll done, okay? If I want to find a 99% confidence interval for what the true proportion of people that support this is, how could I do that? Well, first of all, this is interesting, right? Because if I've got survey data, I want to make sure that I can say with confidence more than 50% of people support this. Maybe if I'm like I'm worried about people, being upset about this or voting for this. I want to make sure my sample, right, would have something over 50% to make sure everyone's kind of more than half the country's in support of this, right? Well, what's my sample proportion here? If 63 out of 81 people were in favor of this, my sample proportion would be 63 divided by 81, right? That's the proportion of people here who favored this. The only other thing I need, well, I have my sample size is 81. The only other thing I'm going to need here is my alpha value. At the 99% confidence interval, my alpha value should be what? So, yeah, 0.01, the area outside the interval in decimal form, right? And kind of these are some benchmark values we're going to see a lot. Anytime I want kind of, what was it? 99%. Anytime I want 99% in my confidence interval, that z-score is always going to be 2.58 that I want to look up. Now I can prove this to you by going here. If alpha is 0.01, for my confidence interval, I actually want to look up alpha divided by 2. So 0.01 divided by 2 is 0.005. So I go to that table, I'm finding what's closest to 0.005. Looks like it's in between these two guys. So negative 2.57 and negative 2.58. We'll use the larger in absolute value, the larger of those, so 2.58. Sure enough, that's kind of one of the benchmark values I told you that we'll see happen a lot when we're wanting the 99% confidence interval. From there, right, I've got my sample proportion, I've got my sample size, alpha, I look up that z value, and this should not be 0.495, this should be 0.995. I just hit a typo, I just must have hit 4 instead of 9 there. Once we have that z value, we could calculate the intermediate step. So instead of doing this all at one time, we could first find that standard deviation of our sample proportions. And now it's just a matter of plugging everything in. All right, we have the z-score, we've got our sample proportion, we found this standard deviation as an intermediate step, and we get this confidence interval, right? Now, instead of doing step 3 and plugging it in, you could just do it all at one time, right? Instead of doing the intermediate step, okay? Now, once we have that confidence interval, thinking a little bit more about the interpretations, what am I really saying here? I'm saying based off the sample evidence that I found, with 99% certainty, I can tell you that the proportion of people who are in favor of supporting pre-existing conditions is between what, 66 and 90%, or a proportion of 0.66 and 0.9? That's pretty high, right? All those values definitely reflect that more than half the population is in favor of this, right? They're all, the true population proportion is definitely one of these values, or 99% certainty is one of these values in this range, which are all over 0.5, right? So I look at this and I'm like, yeah, this is good. Probably something that we want to try to get passed through, right? Any questions on that before we keep moving? I want to do another example, I didn't look up the recent numbers. I might do that and bring them in the next class just to kind of show you what we could do here. So I grabbed this data from the last election. I don't know what, I haven't seen, I should try to look at some of the polls out there right now. But there was a survey, 912 people, 46% said they were going to vote for Clinton in the last election. So this is like prior to the last election. If I wanted a 90% confidence interval for the true proportion of people in the US who are going to vote for Clinton, or were going to vote for Clinton, what would it be? Well, first of all, our sample proportion here is 0.46. It looks like all these are centered around 0.46, so they all seem like viable answers. Right? If there was one that was, for example, 0.42 to 0.44, we know right away that can't be the confidence interval because our confidence interval is centered around whatever our sample statistic is, which is 0.46, okay? So, once again, we've got these benchmark values. If we want the 90% confidence interval, that's going to correspond to this z-score of 1.65. But how can I kind of double check that? Well, if my alpha, right, 90%, my alpha is 0.1, then I'm going to look up alpha over 2, so 0.05. What's the closest thing to 0.05? Looks like it's these two values, negative 1.64 and negative 1.65. We said we don't use that negative sign because it's already built into our confidence interval equation, so 1.65 is the value we'll use. So now we've got everything we need. Right? We got our sample proportion of 0.46, the sample size, we had 912 people in our survey. We got our z-score. We could calculate the intermediate step, which is find the standard deviation of our sample proportions by plugging everything in, right? Sample proportion, sample size. We then throw that into our confidence interval equation, and we get this nice 90% confidence interval. Right? So it's the same procedure as what we're doing with a sample mean. In fact, it's a little bit easier because now we actually only have 3 things that we need to look for, not 4, right? Now, before we had the population variance, sample size, and sample mean. Now all we need are the sample proportion and the sample size, okay? If I plug that in, I find that the 90% confidence level that I could have said between 43 and 48% of the country was going to vote for Clinton, right? In fact, I think this actually includes what the true population actually did. We could actually look real quick. What was the popular vote? Clinton, I'll probably have to search Hillary. Hillary Clinton popular vote 2016. Let's see if they have, let's rely on Wikipedia. Might be a little bit off, but 48.2%, which sure enough, oh man, we just barely got it, right? 48.2%. That confidence interval actually included that, right? So, these polls are definitely useful as long as they're not maybe biased. We talked about some of the biases that could exist because the same poll kind of only found 40% were going to vote for Trump, which notice we have we could go through the same process just using that 0.4, find our confidence interval for Trump. And notice what's interesting here is I can start, when I find 2 confidence intervals, I can then start to make some pretty cool statements. So if for Clinton, it was between 0.43 and about 0.49 was the 90% confidence interval. And for Trump, it was 0.37 to about 0.42. If we think about that, what we're really saying is, well, it was like 48.48 for Clinton and 0.4, let me get these values right. So 0.42, 0.37, 0.43. Okay. So 0.43, 0.42, 0.38 or whatever it was. Now notice with these confidence intervals, because they don't overlap, I know with 90% confidence, the true population proportion for Trump is somewhere in this range. The true population proportion for Clinton is somewhere in this range. So even if it was the lowest possible value here and the highest possible value here, with 90% confidence, I could say the true population proportion of people that will vote for Trump is going to be lower than that of Clinton, right? Now, obviously, that doesn't really matter in our election in the sense that the Electoral College is what really matters, but we could at least make the prediction of the popular vote. In fact, because it's getting close, I'll go out and find a survey, and we'll do that next class, and try to make a prediction for what's going to happen with the popular vote. And sure enough, if we look back at that website, 0.46 and 0.48, sure enough, the true population proportions, right, actually, Trump was lower. Right? So we'll try to do that with some current data next class. I think that's kind of a fun exercise. And also starts to allow us to think about, once I have these confidence intervals, if they overlap, right, I can't actually say that one of them is going to be great, right? But when they don't overlap, I can start to make some statements that with 90% confidence, I know this proportion for Trump would be lower than Clinton. Now, the problem is, if I went out to like the 99% level, what's going to happen to these confidence intervals? They're going to get wider or bigger, right? So if I go out to the 99% level, what actually ends up happening if you work through the math, and these I guess don't really matter, but they also get wider. Well, now when they overlap, it could be the population proportion for Trump is here, and it could have been the population proportion for Clinton is over here, right? Now, so if they overlap, I can't really say that one is higher than the other. But if they don't overlap, now I can start to make some pretty cool statements, okay? Any questions on that before we keep moving? We're okay with that? Okay. Where are we at in time here? Oh, we got plenty of time. So how do we do this in Excel? Right? Now I have two examples here. I thought I did. I guess I only have one. We'll do this one. So I had this enrollment data, and I had created this variable which was, does the school have more than 10,000 graduates, right? So I calculated from that 10 variable. Remember, we said, how do we find a sample proportion in practice in Excel? It's just the mean, or that average of a 10 variable, right? So for these D1 universities, about 79% of them have more than 10,000 10,000 students enrolled, okay? This is enrollment data. I shouldn't have said graduates here. That doesn't make any sense, all right? Because I was creating this from enrollments here, total undergraduates. So I can find my sample size by using that count function. I now have my sample proportion, my sample size. That's all I need other than alpha to build confidence intervals for sample proportions, right? So I go down here, I'm going to delete this and kind of recreate it, right? So here's my 3 alpha values, kind of our benchmark values. Whoops. Wrong cell. Just like with the sample mean, if I know the area I want in the tail, alpha over 2, I can take the absolute value of that norm.s.inv, alpha divided by 2, right? Now here I'm doing it slightly different than I did before. I told you there was 2 methods, so I'm showing you kind of each one. Instead of doing 1 minus alpha over 2, we could just use alpha over 2 and take the absolute value to kind of drop that negative sign. But it's really the same sort of thing we were doing before, right? So now, copy this down, and I've got my 3 z-values. Notice, they should be the same 3 z-values. If I want the same area in that standard normal distribution left tail, I'll always, when I look it up, always find the same z-value, right? So, you should see these numbers all the time. If you're doing your work in Excel and I give you these 3 alpha values and you're not seeing these, you made a mistake somewhere, right? And when we're doing these, and if I give from here on out, when I give you these Excel assignments, do not look these up in the table. I want you to actually use Excel. Like if I give you an individual or Excel assignment, the purpose of those assignments is so you start to get used to using Excel. So for instance, do not put this in there. Do not look it up and put the value in there, right? I want you to be using kind of this Excel. And that doesn't apply to the current individual assignment because we hadn't worked through all of this stuff. And so I'm not saying that for the current individual, if you looked it up, that's okay. But from here on out, any future assignments, because we now can see how we use that norm.s.inv function to build confidence intervals and things like that, I want you to be using Excel for those types of assignments, okay? Any questions on that? Was that clear? Yes, no, yes, okay. So we've got our z-values. Well, now it's just putting in that formula, right? Using Excel as a calculator. I've got my sample proportion. For my lower bound, I'll subtract that z-value, multiply that by the square root of my sample proportion times 1 minus my sample proportion divided by my sample size, right? And all I'm doing there, I was gonna say, do I still have this up on the board? All I'm doing there is entering in this equation and just selecting the cells that have those values in them, okay? So once I have that, right? When I copy this down, I only want the Z value to be updating, so I'm going to freeze everything else. So freeze this, freeze this. There we go. I'll scroll over a little bit so it doesn't look so goofy. Okay. I can then copy these down. I get my 3 lower bounds. How do I get the upper bound? Probably the easiest way, I would say, select this, Control C, hit enter to get out of the cell, Control V. Didn't update my cell reference when I do it that way. Now, the only thing I want to change is instead of subtracting that margin of error, I add that margin of error, right? Everything else stays the same. I copy this down, and I'm done. Right? Same procedure that we used before. Notice the higher the level of confidence I want, right, or lower alpha values, my lower bound gets lower, my upper bound gets higher. Okay? Any questions on any of that? You want to see another cell again, or a question on how I copied something over, or we're okay with that? Double check the chat here. All right. All right, so get rid of that. The next thing we're going to talk about is, I mean, I'm always surprised that nobody calls me out on this, because like at this point you should be thinking about a little bit when we're talking about the sample mean examples. We can't see the population mean, right? That's the whole purpose of building this confidence interval. But we don't have the population mean, but we somehow have the population variance. I think I explained it away with something like, well, yeah, we might know the machine has a certain amount of variance on it or something like that. But for a lot of examples, like how the hell are we gonna have the population variance if we don't have the population mean, right? So a lot of the times we don't know that population variance or the population standard deviation. So what can we do? All we're going to do is replace our population variance in that confidence interval equation with our sample variance, right? It's the best guess of what the population variance is going to be, okay? So once we start using that sample variance, we know that we're going to have a little bit of an issue, right? Because if we go back to thinking about differences between population and sample variances, what would be true about the difference between, or remember for the sample variances, we divided by n-1, right? We said when we have really small sample sizes, that matters a lot. Because if I divide by 2 instead of 3, that changes the number a lot more than if I divide by 999 instead of 1,000, right? So because we have this sample variance now, our sample means won't quite be normally distributed. They'll be very close to a normal distribution, but not quite, okay? So what's going to be true, though, is that they will be distributed with a symmetric distribution, right? Like once we turn these into z-scores, those z-scores won't quite be normally distributed. They're actually going to have what we call a student t-distribution. Now, each one of these student t-distributions, right, there's actually many of them, right, a family of them. Each sample size, where is it? Yeah, so each sample size is going to have a slightly different student t-distribution. So we'll call that, instead of our sample size, we're going to call it our degrees of freedom, right? So n-1 is going to be our degrees of freedom. It's directly related to the sample size, right? n-1. Okay. So these student t-distributions are going to be a little bit more spread out than our standard normal distribution, okay? So they'll have a mean of 0 still, but now the variance will be slightly greater than 1, because we knew the standard normal distribution had a mean 0, variance of 1. Our student t-distributions will all have a mean of 0, but the variances will be a little bit higher than 1. As we get to higher and higher sample sizes, where is this? Yeah. As we get to higher and higher sample sizes, that student t-distribution, the variance gets closer and closer to 1. So if I have any sample size over 100, to the like 3rd or 4th decimal, I can't distinguish any differences between the student t and the standard normal distribution. Now there's still slight differences, but once I get to a sample size over 100, they look really, really similar, right? I mean, very close approximation of the standard of the student t would be using the standard normal distribution, okay? Now, when we have sample sizes less than 100, well, then we start to get greater differences, right? They don't quite look the same. Okay? So what does this look like visually? So if we started out with a standard normal distribution, mean 0, variance of 1, if I looked at a student t distribution where all I had was the sample variance and my sample size, sorry, if my degrees of freedom is 20 here, degrees of freedom is n minus 1, so my sample size would actually be 21, right? So n minus 1 gives me my degrees of freedom. The variance is going to be a little bit higher than 1. So what happens with a higher variance? It kind of flattens our curve, right? The values right around the mean, right? These values, a little less likely. Values further from the mean, a little bit more likely with that student t distribution, okay? So you can kind of think about for confidence intervals, how is this going to mess us up a little bit? Well, now if I want to guarantee that there's, say, 90% within a certain number of standard deviations above and below the mean, well, now in order to get 90, before maybe I could have just cut it here, and the area in between would be 90. Well, now, if I cut it in the same place, now that area is smaller, so I'm going to have to cut it out further, right? I'm going to have to kind of expand how many standard deviations above and below the mean I want to go, right? So we can think about, what if I went to an even lower, degrees of freedom, 5? Well, now you can see it flattens out even more. So think about it this way. If I have that same cutoff score of 1.96, when I was using this black distribution, or the standard normal distribution, the area to the right of that is 0.025. I can look that up in the table, figure out the area to the left, subtract it from 1. The area to the right of 1.96 is 0.025 for that standard normal distribution. But notice when I have flatter distributions, flatter student t distributions, well, now that same value of 1.96, the area to the right of it is going to be more, right? You can kind of see the space in between the blue and the black line, right? I'm getting a greater area in that right tail. Or the probability that I see something 1.96 standard deviations away from the mean or more is now going to be something that's greater than 0.025, right? So if I want that area of 0.025 in the upper right tail, I'm going to have to choose a value that is larger, right? To kind of, reduce that area in the tail down to 0.025. Okay? Here, I'm going to give you, I got a board behind me, so let's do that. I want to really kind of hammer this point home. And I don't really like how close those were. So let's say I've got my standard normal distribution. This area is 0.025, right? Well, I know for student t, it's going to be flatter. So I'm going to really exaggerate this. So let's say my student t looks something like that. Well, now if I use that same 1.96, you can clearly see the area is going to be way larger than 0.025. So in order to get the area back down to 0.025, I'm going to have to use a higher value, right, to get that area to the right of that value to be 0.025. Does that making sense? Okay, so got that hammered down. We're going to start using this thing called the student t table, right? So when I want a certain level in my upper tail, right, the value that would give me that area is going to depend on my degrees of freedom, because my degrees of freedom, remember, flattened or kind of made my distribution more peaked, right? So we'll look at this student t table. Whatever our sample size is, we'll subtract 1 from that and then look up that degrees of freedom. So let's say I had a sample size of 51. My degrees of freedom would then be 51 minus 1, or 50. And then say, okay, what t value now, not z value, because we're not using that standard normal distribution, we're now using a student t distribution. So what t value would give me, say, 0.025 in that upper right tail at a degrees of freedom of 50, 2.01. Remember we said it should be a value that is greater than 1.96, and sure enough it is. Right? As we go to higher and higher degrees of freedom, notice we started out, the area to get 0.025 for low degrees of freedom was as high as 4.3. As we get closer and closer, right, or higher and higher degrees of freedom, we start to get closer and closer to that value of 1.96. Because as we get higher and higher degrees of freedom, the student t distribution starts to look closer and closer to a standard normal. In fact, if we had theoretically an infinite number of degrees of freedom, which would be an infinite sample, we will get exactly the same value that we would see from the standard normal distribution, okay? So notice if we use this last row, these are actually the values we would find from the standard normal table. Right? So from here on out, if you're actually interested in finding those z values, you could use the student t table and just look at this last row that has infinity. Because if it was infinity, the student t for degrees of freedom of infinity is exactly the same as the standard normal. Right? So the actual table that I posted for you guys has a few more lines. So this should be up on Canvas. Take a look at this here to kind of. So alpha now, don't get confused with this. If you want to print this out, cross out this alpha. All alpha is telling you is the area in the tail. When we start to do things like confidence intervals, well, alpha, is what we're thinking about the total area in the tails, not just the area in one tail. So if that gets confusing, just cross this out. This represents, these column headings, the total area just in this upper right tail, okay? So we have our different degrees of freedom. If I wanted 0.025 in that upper right tail at degrees of freedom 1, I would need to use a t value of 12.7. As I get higher and higher degrees of freedom, notice that value starts to get closer and closer to 1.96. Sure enough, once I get down to 1,000, it's 1.962. And at infinity, it's exactly that 1.96, which I would have found using that standard normal distribution, because that last row would be if I had an infinite number of degrees of freedom, okay? So we use this table a little bit different than the standard normal, right? In the sense that now our t values, which are kind of like z values, are in the middle of the table, and the area that we want in the tail is actually our column headings, okay? I mean, theoretically we could do like a 3D table where I was looking at not just degrees of freedom, but I could do, 2 decimals for different levels of t's and then look up the problem, but it's, that would be a mess. So this is kind of be the format of the student t table that we find most useful. And the reason why is because we don't really care about a ton of the area in the tails here. A lot of the times we just want these benchmark values in the tail, right? We want these values for alpha over 2 that correspond to the benchmarks of 90, 95, 99% confidence intervals, okay? Any questions on this table or how we read it? All right, so I think we'll save this for next class. And we'll kind of revisit this, work through some student t distribution examples, probably we'll do some Excel work. I doubt we'll get to these later slides of hypothesis testing. I might just introduce the idea on Friday, but for sure we'll get through some examples for that student t distribution and building confidence intervals when we only have a sample variance, okay? All right, if there's no more questions for me, I will see you guys on Friday.